Hi, ready to go? Okay, so next video here in our functions unit is the greatest integer function. So we've done all those parent functions, we've got piecewise function was the last one, and now we have this thing called the greatest integer function. So after today, hopefully you can evaluate it and graph it. Sometimes this function is called the rounding up or rounding down function, so another name that you could use for this function. So let's take a look at it. The greatest integer function in its form here, if we were to write the equation out, would look like this. It's like a double bracket. So if I were to draw it, I'd have one bracket, two brackets. It's a double bracket on both sides, not to be confused with absolute value or anything like that that uses other brackets or things like that. They're also not parentheses, okay? This just signifies it is a greatest integer function. So what the heck is a greatest integer function? So it's going to look like a piecewise function when you graph it. It's not going to be continuous, and it's going to have a bunch of different pieces that make it up, what the function looks like. The notation, again, these double brackets x, represents the greatest integer less than or equal to x. So it's the greatest integer less than or equal to x. The one thing to note about the greatest integer function is your output will never be decimals or fractions. Your outputs will always be integers. So before I pull out this third piece, I want to jump down to the bottom here. It says evaluating greatest integer function. So it says evaluate the greatest integer function for each value of x. So say for each one, I were to plug the input or the x value that I have written here into the greatest integer function. Well, if you put 4 as an integer, it's a whole number, the output would just be 4, okay? Same thing with negative 5. If I put negative 5 into this new function here, I get negative 5 out. So when you put integers in, you get integers out. That's easy. Now this is not an integer, this is a decimal, okay? So if I were to put this into the greatest integer function here, okay, it's called, there it says, it represents the greatest integer less than or equal to it. So if I think of a number line, I think that's the easiest way to do this. If I have a number line, that's 0, there's 1, let me space this out a little better actually. So if I think of a number line, I'm just going to put 0 here, 1, 2, 3, 4, and so on. 2.76 would be right about there, right? 2.76 would be right about there. So if I'm putting 2.76 into the greatest integer function, my output's going to be a 2. And that's because it's the greatest integer less than or equal to it. So if this is it, what is the greatest integer less than or equal to it? Well, you'd have to kind of go back to 2. So it's kind of like you're chopping off the decimal piece. Okay? So 2 point anything would basically round down to 2. Okay? That's why sometimes it's called the rounding down function. So if I had 2.3, it'd round down to 2. If I had 2.99999, it wouldn't be 3, it would actually just be 2. So you're taking the integer that is just less than this non-integer number. D, let's do D here. Well, D is pi. Pi is 3.14, right? Whoops. 3.14. 3.14 is right around here, right? So if that's where 3.14 is, if I put this into the greatest integer function, I would get 3. It's the greatest integer less than 3.14. Now this one's interesting. Let's take a look at negative 6.5. And again, I'm going to kind of show you this with a number line. Negatives can be a little tricky here. So I'm just going to put negative 6, negative 5, negative 4, and so on. So here's a number line, right? Negative 6.5 would be right about here, right? Now if I am putting negative 6.5 into the greatest integer function, remember it's like the rounding down. So the answer wouldn't be negative 6. What is the integer that is less than negative 6.5? It would actually be negative 7. Okay, so that's a little tricky. Remember, negatives are kind of in reverse order there. So if I'm rounding down from negative 6.5, my answer would be negative 7. Okay, so again, your answers aren't going to be decimals, fractions. It always just rounds down to the integer that is just below it. And one last thing here. The greatest integer function is sometimes called the rounding down function. Just like I said here, like 2.76, we'll bring it back down to 2. 3.14, bring it back down to 3. Okay? Not sure why I didn't put 4 there. But anyway. Okay, moving on. So you got to be able to evaluate it, and it's just that simple. Now how do we graph this guy? So if I had the function f of x equals the greatest integer function of x, again, we like to have a set of parent points. The set of parent points for the greatest integer function are the same parent points that you would have for a linear function. So that's pretty simple. So it represents the, it's the same thing as f of x equals just plain old x. It looks the same as far as the table goes. So I'm going to go ahead and graph those ordered pairs. -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. Now, here's where it differs from your basic linear function. Another name for this, sometimes we call it the step function. And here's why. Remember, your output's never going to be a fraction or a decimal. It's just going to be integers. So your integers on your y-axis are, right here on the grid lines, right? So you can't have any graph that is in between integers. So this space between grid lines, where, like in between here and here is between 0 and 1. So like 0.5 and 0.4 or 0.8 or whatever's in between here, you're never going to have any outputs along that range. So it's called a step function because to graph this, you would literally create a step with an open circle underneath your next x value, your next ordered pair, and then you would continue that pattern going up because your output is always going to be an integer. So to create the graph, you would graph your basic identity function, -2, 2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and you would draw a horizontal line extending all the way till you're below the next ordered pair, and then you put an open circle. Okay? So that's how you create step function. Now, we've only graphed 5 steps here, but you could continue to make steps going up and going down. So to signify that, we do a dashed line in both directions just to show that it continues on in either direction. Okay? But all you're required to do is you have to do at least 5 steps there. Okay? So let's talk about the domain and range here. Domain, again, this isn't a continuous function, but the domain is still -infinity to infinity. Every x value is accounted for. So if I'm here, now I'm jumping up at -1. Now I'm jumping up at 0 and so on. So the domain is -infinity to infinity. It's the range that's a little tricky. Notice there's a lot of holes in the range here. But again, it is kind of simple because your outputs are only integers, right? So we're just going to put the range as the set of integers. So you can't really write in interval notation a whole bunch of integers. It doesn't work that way. So we'll just put the set of integers. Is it continuous? No, it is definitely not continuous. Okay? So that's your parent function. So now let's expand on that and let's actually apply some different transformations here. So look at it just like you would any of your other parent functions. If I look at this function, I've got 2 things going on, right? I've got a vertical stretch. Interesting. I've got a vertical stretch, right, of factor 3 or magnitude 3. And I've also got a shift right 2 units. So again, I just read that like I would any transformation on any of my other parent functions. How do we go from there? Remember, let's make a table. Parent points, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. Those are my parent points. Now, I am going to do 2 transformations here. I'm going to start with my x one. I'm going to shift to the right 2, so I'm going to add 2 to all my x's. And I'm going to take all my y's and multiply by 3 for that vertical stretch. And again, this is nothing new. This is what we've done with every other parent function. So let's apply those changes. So I'd be at 0, 1, 2, 3, and 4, right? And when I multiply by 3, -6, -3, and so on. So here are my new x's, here are my new y's. Again, I'm seeing nothing new or nothing different from what we've done in the past. So let's go ahead and graph these guys. Okay? I'm going to go ahead and graph. I've got 0, -6, 1, 2, 3, 4, 5, 6. I've got 1, -3, 2, 0, 3, 3, and 4, 6. Now again, I'm not going to draw a line through it. It's not a linear equation. It's a step function, greatest integer function. So I am going to extend a horizontal line until I'm underneath my next ordered pair. Finish it with an open circle. Extend, open circle. Extend, open circle, and so on. How do you know where this ends? Well, if you look, every single step is 1 unit long. So extend, open circle. So we would look like this. And that's it. So just remember, you should never be connecting your ordered pairs. You're always creating these steps afterwards. Okay? Now, step functions actually represent a lot of real-world problems that we can run into. So here's one application that would make sense if we wanted to graph, if we wanted to show a visual graphically of this application. It would be a step function. So let's take a look. Parking rates. If you want to park downtown at some garage, this looks like it's a pretty cheap garage for the city. Downtown parking charges a $5 base fee for parking through 1 hour. So you're parking for 1 hour, more or less, it's $5. It is $1 for each additional hour or fraction thereof. So the second you are over an hour, you're getting charged another buck. It could be 1 second over an hour. It could be 59 minutes over an hour. It's just one additional dollar until you get to the next full hour. Okay? You're never going to be charged more than $15 within 24 hours. So let's sketch a graph to represent this application here. So I've gone ahead and I've got a grid. I've already kind of numbered my x and y axis. My x axis is going to be every little grid line is 1 unit. Same with my y axis. So if I were to graph this guy, okay, we've got 0 here. Now at 0, you haven't parked yet. So I would put an open circle there. And then for the first hour, it's going to cost $5, right? Including 1 hour. Now this is a little different. You know, our normal step function starts with filled in, open. This one's open, filled in, because on 1 hour, it is still $5. So depending on the application, you know, the open and closed circles could be switched around. So the second you're over an hour, you're getting another $1, right? So open circle on 1, representing I'm going right after 1, to the second hour would be $6. And then, like it says, every additional hour is an extra $1. So open, 1 more hour. Open, 1 more hour, and so on. This trend is going to continue until I do the maximum, which it says. Your maximum you would ever pay in 24 hours is $15. So as soon as I get to $15, okay, so now I'm on $15, right? And that is what? 8 hours later. 5, 6, 7, 8 hours later, I'm now at $15. But I'm never going to, but when I get to the next hour, I'm not going to go to 16 because it says the maximum is $15. So now once I'm at 15, I'm going to go all the way through. And it says, and the situation stops at 24 hours, so I'll just end my graph there. Okay? So that's not a simple graph like this was. It kind of changed the steps and everything. You've swapped your open and closed circles. That last one is extended because that's the situation you were given. So you kind of have to read the application pretty carefully to know how to form your steps. But this would be a graphical representation of this parking situation. So once again, you got to be able to just evaluate. Like if you know you're doing a greatest integer and it's 2.76, you know the answer is 2. And you also need to know your parent function so you can actually graph a step function and then hopefully apply it to some applications. So good luck.